Hello. In the previous video, I presented a summary of the idea and the theory behind the logistic regression topic. And today I would like to talk about the cost function of the logistic regression. So if you remember the cost function or the error function of the linear regression, it takes the formula that you can see here. It is simply the summation of differences between the true values of the target variable y super I minus the linear model that we are looking for, defined by the function of x super I and the set of coefficients w. So this was the simple error function that we have used in order to compute the linear regression model. In the logistic regression, we take the same formula. However, we replace the linear hypothesis within the linear regression model with a new logistic hypothesis. We call it here G of x super I and w, where G of x super I and w equals the logistic function that we have discussed in the first video of this tutorial, equals 1 divided by 1 plus e to the power of minus w transpose x super I. And the goal is to minimize the new error function, or we call it the new cost function here, using the new notation of the g of x super I and w. So having a look at the logistic function, we can find that here the red function here, the red curve here, represents a sample logistic function defined by this equation, and the purple function represents its first derivative. And as you can see here from the plot, that the first derivative of the logistic function can have a lot of trends up and down, which means it has multiple maximum and multiple minimum values. And this is a non-desirable feature of the error function that we try to minimize, or we try to optimize, because it can happen that the method we use to minimizing such function can reach a local minimum rather than a global minimum, which will accordingly generate an inaccurate classifier. So we need a way to transform our logistic function into a convex function, or a function with a single minimum value, such that we can optimize it in a way we are guaranteed that we have reached its minimum value of the first derivative. So the solution to this issue is by using what we call the likelihood function. Likelihood functions are very popular functions in the area of probabilities and the area of Bayesian inference. And today we will make use of it in order to reach a formula that is guaranteed that it has a single global minimum or maximum. So one point I want to refer here about before going into the details of likelihood function is that we need to distinguish between the regression problems and the classification problems. In the regression problems, where we try to predict a target variable which contains some continuous values, like the height of a group of persons or weight of a group of persons, we have designed an error function, and we always trying to minimize this error function, which means we're trying to minimize the summation of distances between the true values of the training data set and the generated model. On the other hand, within the classification problems, like the case of logistic regression, we can do both things. We can either minimize or maximize the cost function. In case of the function correctly classified the target variable y, which means if the true value of y is 1 and the learning model generates 1, and the other way around, if the correct value is 0 and the model generates 0, then we need to minimize the cost function or the penalty function in order to optimize our classification model. On the other hand, we can also maximize the cost function, and in some cases the cost function here is called the penalty function. We need to maximize this penalty function if the generated model misclassified the target variable y. So we can say that if the true value of y is equal 1 and the model generates 0, or the other way around, then we need to maximize the penalty or maximize the cost of our function, such that we try again to optimize the performance of our generated classifier or of our generated classification model. Now let's get back to the mathematical definition of our probabilistic model. In the previous video, we have seen that we can use the probability or the logistic function, which can express by the probability that the target values equal to 1 given the predictor x and the set of coefficients w, and we can define it into two lines here. We can say that it is equal to g of x and w. The g of x and w again is equal to the logistic regression function if the true value of the target variable is equal to 1, and it can equal to 1 minus the g of x and w if the true value equals to 0, where here the g of x and w equals the probability that the outcome equals to 1, which is our regression function. So we can put these two lines into one single line. We can say that the probability of y given x and w equals g of x and w to the power of y multiplied by 1 minus g of x and w to the power of 1 minus y. Of course, you can easily conclude that if y equals to 1, the expression is ended to this single value, and this value will be deleted, and if y equals 0, then this value will equal to 1, and we end up with the second definition or the second possibility of this model. Actually, as a side note, this function is nothing but the probability mass function of the very popular Bernoulli distribution. This is a very well-known probabilistic distribution, a standard probabilistic distribution. And accordingly, we define the likelihood of the set of coefficients w given the predictor x as the probability of the target variable y given both predictor x and the set of coefficients w, which is equal to the probability of x given the set of coefficients w. So I don't want to get into a lot of details about this formula of likelihood function, but what I want to mention here that firstly you need to know that the likelihood function is a function of coefficients but not a function of our data x. The second point that I want you to know is that the likelihood function is not a pure probabilistic function, but it is proportional to a probabilistic function. So here we set it to the probabilistic value of x given w, which is the simple way of the Bayesian inference, but I will not go into much detail about the Bayesian inference in this video. But this is what you need to know, that in general the likelihood function is not a probabilistic function, and it does not have to sum up to 1, but in our topic today we treat the likelihood function as a probabilistic function, but it is a function of coefficients, not about the data x. So, according to the theory of probabilities, we knew that if our set of predictors are IID, which means that they are independent and identically distributed, like in our example, if we have a group of persons, we know that the gender of one person is independent and independent from the gender of all of other persons. So in this case, if we want to compute the probability of predictor x given a set of coefficients w, then this probability function is equal to the product of the probability of each individual xi inside this predictor by itself. So we can expand the expression of likelihood function to be that the likelihood of w given x equals the product of the probability of each observation, of each true value of observation I, given the predictor, the corresponding predictor xi and w, which is equal to, again we replace this probability model with its g notation. So it's equal to the product of g of x super I and w to the power of y super I multiplied by y minus j of x super I and w to the power of 1 minus y super I. Actually, we have a lot of problems with this definition of likelihood function, because here we're trying to multiply a lot of probability values, which means we try to multiply a lot of values between 0 and 1. And if you try to multiply 100 values, or maybe less than 100 values of probabilities between 0 and 1, you can end up with a value of 0, or a value very close to 0. And this is not helpful from the computational point of view. So we try to have more meaningful value of the likelihood, and therefore we want to convert the product signal to a summation signal. And in order to convert the product to the summation, we take the logarithm of the likelihood. We call it the logarithm of L of W given x here, and it is equal to the summation. Then when the log enters this expression, it will convert the product to the summation, and we will get this power as multiplied by the log of the internal function. So we will have that the log likelihood equals the summation of y super I multiplied by the log of g of x super I and w plus y minus I super I multiplied by the log of 1 minus g of x super I and w. And of course the product signal here is converted to the plus signal. Now, as we obtain the log likelihood function of the set of coefficients w given predictors x, now the question would be, should we maximize the log likelihood or should we minimize it? Actually, as I mentioned earlier in this video, we can do both things depending on the visualization that you can plot your log likelihood. So in order to have better understanding of this point, we would like, or I would like to divide the log likelihood once again into two lines. So I will set the first line to the log j of x super I and w in case of y super I equals to 1, and to the log of 1 minus j of x super I and w in case y super I equals to 0. And again, in each expression, you will end up using, so if you substitute yi with either 1 or 0, you will end up with these two values of the log likelihood. So now, if you want to maximize the log likelihood function, we can see it from here visually, that in case we have the target value y, the true value equals to 1, then here I am plotting the predicted value g of x super I and w on the x-axis, and the cost function, the log likelihood, on the y-axis. So in case we have the true value of y super I equals 1 and the predicted value also equals to 1, then we have the cost value or the log likelihood equals to 0, which is the optimum result that we are looking for. However, if the true value equals to 1 and the predicted value is trying to moving to the other way, to moving to 0, then we will find that the corresponded log likelihood is moving to minus infinity. And in this case, we are trying to maximize the value of log likelihood in order to approach this extreme value where the predicted output is typical to the or close to the true output. So here we are trying to maximize this value in order to approach the correct value of classification with the predicted value. The same thing with when the true value is equal to 0. As you can see here, if the true value equals to 0 and the predicted value also equals to 0, then also the cost function equals to 0. However, if the true value equals to 0 and the predicted value is trying to move away from the 0 value, so the corresponded log likelihood function is going to the minus infinity value. And again, in this case, we are trying to maximize the log likelihood in order to approach the correct results of our classifier. But also we can minimize the log likelihood in case we switch the signal of the log likelihood. So if we put minus log instead of plus log in the last slide, if we put minus log of g of x super I and w in case of y equals to 1, so here if the true value equals to 1 and the predicted value equals to 1, then the cost function, the log likelihood, also equals to 0. But if the predicted value started to move to the value of 0, the corresponding cost function will move to plus infinity. And in this particular case, we're trying to minimize the cost function again to return it to our corrected classification case. The same thing also when the true value of y equals to 0. Again, it is the cost function equals to 0 if the prediction is typical to the true value, both equals to 0. But if the prediction moves to the value of 1, again the corresponded log likelihood will go to plus infinity, and in this case we're trying to minimize the log likelihood. So as I mentioned before, you can do both sides as long as you control the signal of your log likelihood function. You can either maximize it or minimize it, and both the results of both scenarios are identical. So now after we learned about the likelihood function, now we try to minimize it by computing the first derivative with respect to each coefficient wj, and try to follow with the optimization of our cost function. So this is the definition of our log likelihood function: y super I log of g of x super I and w plus 1 minus y super I multiplied by the logarithm of 1 minus g of x super I and w. We need to differentiate this term with respect to wj. So remember then that if you want to differentiate a logarithm function, the derivative equals to 1 divided by the value inside the logarithm multiplied by the derivative of the function itself by the coefficient x. So the derivative of log likelihood in this case will be y super I divided by the value inside the log divided by g of x super I and w multiplied by the derivative of g of x super I and w with respect to wj plus y minus I divided by 1 minus g of x super I and w multiplied by the derivative of minus g of x super I and w with respect to wj. In the second line we just send this minus signal outside here such that we have it in this form. And now if you remember that the function g of x super I and w is actually a nested function, which means that it contains the logistic function g of x super I and w contains another linear function f of x super I and w. So if you want to differentiate g of x super I and w with respect to wj, we will use famous rule of differentiation called the chain rule, which is states that the derivative of g of x super I and w equals the derivative of g of x of f of x super I and w with respect to wj, which is equal to the derivative of g of x super I and w divided by f of x super I and w multiplied by the derivative of f x super I and w with respect to wj. Again, I'm putting here the definition of our logistic function, which is called 1 divided by 1 plus e to the power of minus w transpose x, where f of x here is or the f of x here is nothing but the linear function w transpose x of super I. So for simplicity, we will try to simplify the term g of x super I and w as g of z. So we introduce a temporal variable z here for to simplify the mathematics. So we'll call that the g of x super I and w equals 1 divided by 1 plus e to the power of minus w t x to the super I. We set the w transpose x super I to the z, so we'll rewrite this as 1 divided by 1 plus e of to the power of minus z, or we can call it simply it's called as g of z. Now if you want to compute the derivative of g of x super I and w by the f of x super I and w, we simplify it as the derivative of or the differentiation of g of z divided by the value of z. When you start to differentiate the g of z here, you will end up with the 1 divided by this value. So 1 divided by 1 plus e to the power of minus z, all square because it is multiplied 2 times. You will divide the function by 1 divided by this value. So you multiply the denominator by itself, and you will compute the derivative of the function, which will be e to the power of minus z. So this expression, you can put this value, this term inside the square into 2 times here, so it will be 1 divided by 1 plus e to the power of minus z multiplied by e to the power of minus z divided by 1 plus e to the power of minus z equals to this term will be the same, and here we will add 1 and subtract 1 again, so we didn't do anything about the expression itself, but we did this because we need to take this part as 1 minus 1 divided by 1 plus e to the power of minus z. And as you can see here that 1 divided by 1 plus e to the power of minus z is nothing by the value of g of z that we have defined before, and 1 minus this expression is nothing but the 1 minus g of z. So we end up by the first term of this derivative as the g of z multiplied by 1 minus g of z. This is the solution of the first part. Now we move to the second part, this one. The derivative of f of x to the power of super I and w with respect to the w of j is computed simply as the derivative of w transpose x super I with respect to w of j, and the w transpose with respect to a single variable inside the vector of coefficients. We can write it as the wj multiplied by x or super I, because all of other coefficients will be deleted because they has nothing to do with respect to w of j, and when you differentiate wj x super I with respect to wj, it will end up equals to x super I. So now we have both these terms, we have computed both of these terms. Now we can say that the derivative of g of x super I and w with respect to wj equals to the derivative of z value with respect to wj, which equals to the g of z multiplied by 1 minus g of z multiplied by x super I. Now we will substitute in the basic log likelihood function. So we will say that the derivative of log likelihood with respect to wj equals this old expression. We will substitute this partial derivative term with the new term that we have calculated now with this term. So we will have here y super I divided by g of x super I and w, which is g of z, multiplied by g of z 1 minus g of z multiplied by x super I minus the 1 minus I super I divided by 1 minus g of z again multiplied by the same term here, g of z multiplied by 1 minus g of z multiplied by x super I. We simplify the generated equation, so we'll have here y super I, this will delete this term, multiplied by 1 minus g of z multiplied by x super I minus 1 minus I super I multiplied by g of z, because this term will be deleted, and here we take this x super I outside the brackets, so it is multiplied by both terms inside the brackets. Again we will multiply the y super I inside here, so it is equal to 1 y super I minus y super I g of z minus g of z plus y super I g of z multiplied by x super I. Here these both terms will be deleted, so we end up by the summation of y super I minus g of z multiplied by x equals y super I minus g of x super I w. Now we will return back to the x and w notation, not with the z notation, multiplied by x. And this is the most interesting point about the log likelihood function, is that when you compare the derivative of log likelihood function within the logistic regression model, you will find that the output is typical to the derivative of the error function of the linear regression. The only difference between both derivatives is within the hypothesis. Within the linear regression we have a linear hypothesis f of x super I and w, But with the logistic regression, we have, or within the log likelihood function of the logistic regression, we have instead the g of x over I and w, which is the logistic function we are using within the logistic regression model. So we conclude that the log likelihood function is typical to the linear regression error function. The difference is only about the hypothesis component. And this is the maybe the tricky point that many of you cannot get easily. So I meant to explain it into very much detail. I hope you didn't get bored of this mathematics. And in the next video, I will talk about how we can use different methods in order to find the best values of coefficients and to find our best logistic regression model. So thank you for your time.